So we're going to look at 3 examples here with kind of the more basic forms of our trigonometric equations. We're just going to have a single function to work with here. It's going to be the functions that we're used to working with the inverse for. Now I did mix up, some of these will need the calculator to help us out, and some of them we can solve with just the unit circle. So we'll kind of see how we switch between those 2 ideas. All right. So this first one, I want to solve cosine of t is equal to 0.3. So what I want to do is rearrange this equation so that it's just t equals. Again, in that last video, I kind of mentioned 2 ways to think of it. You could think of it as just kind of transitioning to the inverse notation, or you could think of it as taking the inverse of both sides. So like taking inverse cosine of both sides is just over here, the inverse with the original function would cancel each other out and leave you with just the angle. But then we'd have this inverse cosine of 0.3. Now, when I look for this kind of input for my inverse function, I'm looking for those special values or those special coordinates from our unit circle. This value is not special. So that tells me I'm going to need my calculator. I'm going to need my calculator to help me out here. If I could spell calculator, calculator. All right. So before I jump to the calculator though, what I could do is go to my unit circle so I can get an idea of what values I'm looking for. So again, I'm solving for angle measurements here. I want to know what angle works so I get this x coordinate of positive 0.3. So if I have my unit circle, this is an x value of positive 0.3, and just keep in mind that I'm looking for all possible solutions here. So if I visualize x equals 0.3, well, here's x equals 1, here's x equals 0, so 0.3 is kind of close to a third. So maybe I'll say about there is positive 0.3 for x. So there's going to be 2 possibilities. So I'm looking for these 2 angle measurements here. So we're going to have an angle measurement that goes to there. We're also going to have an angle measurement that goes to there. Or in fact, we could even go like this. This is shorter. Let's visualize it that way. We'll talk about that other direction as well. But for now, I'm going to think of it in terms of this. So 2 possible solutions, but I'm going to be plugging this into my calculator, and my calculator is going to give me just 1 number. So I need to keep in mind that when we work with the calculator, it's using the fact that inverse cosine is stuck between 0 and pi. So the calculator is going to give me this solution. It's going to give me that angle measurement. Then what I'll need to use is symmetry and kind of the idea of reference angles in order to fill in the blank there. So let's go to our calculator. Make sure you're in radian mode. So we're in radian mode. Unless it specifies otherwise, we're only working in radians here. And I want inverse cosine of 0.3. So that's giving me an angle measurement of 1.2661. So that is this measurement right here. Now with radians, because we're more used to degree measurements, it's just what we kind of, like radians in this course is probably the first time you've been working with radians. Like in degree measurements, we're used to the fact that this is 0 and 90. So if we had some angle measurement of like 75 degrees there, we'd have this instinct of like, yeah, that's right. Just some key values to keep in mind in terms of radians. Like here is 0 radians. This is pi over 2, which in decimal is 1.57. So just so you can get some instinct there, like, okay, that being 1.26 makes sense because it's fairly close to 1.57, just a little bit less. And then over here is pi. Down here is 3 pi over 2. And then we'd be back at 2 pi, which is like 6.28. So just as you're solving these angle measurements, I wanted to draw these here just so that if you're kind of like, is 1.2661 right? We're just getting that from the calculator, does it make sense? You could think of it in terms of a scale of radians and kind of checking that these values are landing where you expect them to. All right, so if this is positive 1.2661, then this green one right here is just going to be the negative version of that number. So negative 1.2661. So we have these two terminal sides, these two angle measurements. Now, writing out the possible solutions, and I'm going to focus on 0 to 2 pi first. So on 0 to 2 pi, and you might see this with a square bracket or parentheses. Either is fine. When it's parentheses, it's just saying it's not including it, so that like if the angle 0 was your solution, then you wouldn't include 2 pi. It's just a little notation thing. So you'll kind of see it switch back and forth. So that positive 1.2661 is in that interval, so that works great. So that's one solution, but then I need to describe my other solution. Now this negative 1.2661 is not in these bounds because it went the other direction. So this is where I would need to think about how to get there, but in a positive direction, kind of like I drew that angle the first time. Or it's the idea of what's coterminal with the negative 1.2661. So how you could visualize that is taking 2 pi minus that value, or you could even think of it as being at that value and then adding 2 pi. Few ways to go about it. I'm going to think of it as 2 pi minus 1.2661 to get to that angle measurement. So that'll give us t equals, then we have 5.0171. So that angle measurement there, again, that makes sense in terms of being between 4.7 and 6.28 as a radian measurement. That's perfect. And it's in that increment of 0 to 2 pi. So that's our set of solutions just from 0 to 2 pi. Now my next piece is to make formulas for it. And there's two ways we can go about it. There's the long way and the short way. So I'll go the long way first with it and then the short way with it. So how I described it in the last video is that we want to kind of have the starting value and then think about just kind of making revolutions around that value. So like moving increments of 2 pi in this case, since we're working with cosine, we have a period of 2 pi. So what we could do is say we'll have a set of values for this angle t, and t can equal 1.2661 plus any increment of 2 pi. And then we have that other angle measurement, so or we have, and we could use the 5.0171, so t could be equal to that value, plus any increment of 2 pi, where k is an integer. So that's one way you can follow it. Just take that value and adding 2 pi since that's our period, and then it has to happen for the other value as well. A more concise way to write it, so a shorter way, is we could say t and t equals, instead of using the 5.0171, we could have used this coterminal angle of negative 1.2661. So really it's that we have the positive form and negative form of that same angle. So we could write this as plus or minus 1.2661 plus any increment of 2 pi k. So we have this kind of short way of writing our angle there, and it's because we have the positive version and negative version. Now we couldn't have done that in the last video, but in these cases where we're symmetric across the x-axis, we can have this shortened form and just can be a bit easier. But they're both correct. Both of them get at the idea of having these solutions. It describes the same solutions exactly. It just appears a little differently. So whichever your brain likes best, go that route. This is kind of tried and true and will work for pretty much every scenario. This is kind of a special case where we're symmetric across the x-axis, so we have this nice positive-negative relationship. All right, so with that, inverse, looked at our unit circle, found all possible solutions, but just focused on that increment 0 to 2 pi, and then we made our formula. Okay. Here, what we want to do is isolate our trig function. We want to get it all alone on one side of the equation. So I'm going to subtract 3 from both sides. So I'll have 4 sine t, and then 1 minus 3 is a negative 2. Divide both sides by 4. So we'll have sine of t is equal to negative 1/2. And I'm going to switch to my inverse format, which would give me t equals inverse sine of negative 1/2. So just getting my angle measurement outside of the function, but then with that I need to use the inverse on the other side. All right, going to our unit circle. This is a special value, so I'm not going to need to use the calculator for this one. I can have some exact solutions. So negative 1/2 is our y value. So that's going to put us about here and here. That's our negative 1/2. So we're going to have two solutions within our unit circle. And my lines are a little off there. So two angle measurements. We can have this angle measurement here, which would be a negative pi over 6. And we would have this angle measurement here, which is, let's see, 1, 2, 3, 4, 5, 6, 7 pi over 6. So in terms of on 0 to 2 pi, the possible solutions would be, so that negative pi over 6, I'm going to need to think of the coterminal angle. So I'll have that 7 pi over 6, or t can equal, that would be the 11 pi over 6. And if it helps, I'm still kind of counting around the circle, so thinking 1, 2, 3, 4, 5, 6. So there's our 7, 8, 9, 10, 11. So when you hear me counting to myself, that's what I'm visualizing here as I go around the circle from when we learned the unit circle. All right, so there's our solutions from 0 to 2 pi. Now what I'm going to do is create a formula to describe all possible solutions. So we're working with t, and then I'm going to have t equals. Now, this case, it doesn't have that nice symmetry like we saw in that last scenario. So this one, I'm definitely going to have those two separate equations. And we're working with sine here. So the period is just 2 pi. So with that, I have my two starting values, and I just want every increment of 2 pi away from those values. So 7 pi over 6 plus increments of 2 pi, or 11 pi over 6 plus increments of 2 pi. And then we just need to explain that k is represented by an integer. And that's that. All right, tangent. One last one here. I'm going to divide both sides by negative 3 so that I get tangent all alone on one side of the equation. I'm going to have tangent of c is equal to negative 2/3, which means c is equal to inverse tangent of negative 2/3. Now, with this one, first thing I'm going to notice is that negative 2/3, that's not one of our special values that we talked about, so I'm going to need the calculator for this one. I can make a little note here that this one needs a calculator. So, drawing a circle here, and what's going to be easiest is with tangent. I'm not really working with the unit circle. It changes a little bit. When we had our our special values that came from our triangles that we're used to on the unit circle. Then we're working with the unit circle, but here it's a little different because what I'm doing is I'm thinking of how tangent represents y over x. And we have some possibilities here. So with that negative 2/3, that negative could be in the numerator. So that would be a negative 2/3, which would mean that's giving me the coordinate +3, -2. But that negative also could have been in the denominator, meaning numerator of +2, denominator of -3, which would have given us the coordinate 2, -3. Nope, -3, 2. Did I switch these around? 3, -2, -3, 2. Sorry, it's hard with that y over x order there. So this isn't a unit circle, it's just a circle. But what we're going to do is think of it as whatever our radius is, we don't even know what it is. It's just that we're going to have this -3 and +2 and +3, -2. So just to kind of visualize where these are landing without measuring exactly, it ends up doing this. And this is a property of what happens with tangent. And it's because with tangent, our period is equal to pi, that when we land on these values for just tangent of an angle, it's going to make a straight line. So really this should be doing something like this because of that property of a period of pi. Because remember, if like this is 0, this is pi. Going 180 degrees is the same thing as going a distance of pi. Same thing here. So it's like to make that 180, it makes a straight line. All right, so solving here, I'm going to need to use the calculator, and I just need to keep in mind that when I go to the calculator, it's only looking at values within that set right there. It says tangents between 0 and -pi/2 to +pi/2. So what the calculator is going to give me is this distance right here. Let's go to the calculator, and I want inverse tangent of -2/3, which is a -0.588. All right, so there's one of my angles. Now what I need is this other angle. And this is where reference angles come in, because that measurement of -0.588 is showing up over here. It's just coming through as this measurement right here. So where I'm solving for this green angle measurement, how I could think of that is I want to go this distance of pi, but then I want to take back that 0.588. So how I'm going to calculate this is going that distance of pi, but then take out that angle of 0.588. So if you get these negative angle measurements here that are shorter, you'll have to use them as a reference angle and keep in mind those kind of like go to pi but then go back, or go to pi and then add some on, and things like that. So that should be a 2.5536. All right, so angle measurements. My possibilities, so on 0 to 2 pi, we could have that 2.5536. We could have, I can't use that -0.588 because that's not within that interval there, but I can use the coterminal angle. So I'm just going to use 2 pi minus the 0.588, which is 5.6952. So there are my two possibilities from 0 to 2 pi. Now, our formula for this one is a bit different because of the properties of tangent and how our period has changed to a period of pi. So what I could do is, and you can start with any of the angles. Let's say I start with this 2.55 0.5536. Let's say I call that my starting angle. You could also argue, well, not argue, but you could also say you want to use that angle because it's like smaller, it's more concise. That's fine too. In fact, that's might even be a more exact answer. So you could have that as your starting angle. Either way, it all lands at the same spot. So what I want to do, like to describe my increments here, so I have my starting point here. What I can do is map to this one by going a distance of pi. And then in terms of coterminal, I need to go a distance of pi, go a distance of pi, go a distance. I can keep landing at those terminal sides if I add on increments of pi or take away increments of pi. So my notation changes here a little bit in that we're not using 2 pi, we're using just pi because of the period. Okay. And I don't need to do a second one. I don't need to describe a second set because when I move by pi, it lands on top of itself. Whereas up here, that wasn't the case. I wasn't able to map from one of these to the other. It was more of just focusing on one and just making a complete circle around that one and just passing over that one, because then we had a second equation that worked with revolutions around that point. So with this one, we just have that starting point, whichever one you choose, move by increments of pi, and that is done. All right, so that's our process for those. Solve for that angle measurement, get it in terms of an inverse function. Take a look at the unit circle. You might need to use a calculator or you can use our special values. Make sure you're grabbing all possible solutions that are popping up on that unit circle, or like in this last case, it wasn't a unit circle, but just a circle. And then from there, list your solutions from 0 to 2 pi, and then from there, create your formula.